Okay, welcome back to another video. So, I'm basically making this video almost directly after I made last video. So, it's a similar problem, also related to number theory. How many divisors of 8400 have at least 4 factors? Okay, so first, let's notice that 1, let's notice that 1 has only one factor, or divisor, doesn't matter. And let's notice that any prime number number this any prime number has well two factors or divisors. And finally, I can easily prove this here. Squares of primes, this just has 3 factors. This is the only value which has 3 factors. These are the only values which have 3 factors or divisors. Okay, so now our goal is essentially to find all of the squares of primes and all of the prime factors within 8400. And we can directly, and since every number is a factor, has a factor of 1, then we can directly eliminate 1. And we'll use the formula that we found last time to find the total number of divisors of 8400. And let me prove this real quick. So this statement here. The squares of primes all have 3 factors. So let's do a proof here. So let's bring up the question. What are the only numbers which have 3 factors? So let's let n equal, I'm using a similar format here. E1 times P2 E2 PK EK. Okay. And we know that we want our number of factors to be 3. So notice that our function t, which we defined earlier, t of n must equal 3, and that must equal, well, e1 plus 1, e2 plus 1, all the way to ek plus 1. And notice that 3 is prime, so the only way we can separate 3 into 2 numbers is 1 times 3, or 3 times 1, since it's commutative. So as a result, we have that this directly translates to the fact that e1 is just equal to 2. So 2 plus 1, that gives us 3, and then finally 0 plus 1 to give us 1, and we can just ignore this here. So we just get that e1 equals 2, and that's our only non-zero exponent. So as a result, we just get that n equals any prime number p1 squared. So as a result, we've just shown that n, which only has 3 factors, is just the square of any prime number. So that was a basic proof. And now, what we're going to do is continue with the problem. So what we can do is we can just find the prime factorization of 840, and that will give us all the prime factors of 840, and we'll see if any of those have their square counterparts. So 8400 equals, well, we have 84 times 2 squared times 5 squared, which is this 100. This part is 100, which is just equal to 28 times 3. So 28 times 3. So 2 to the 4 times 3, I'm pretty sure. So this is just 28 times 3. So yeah, so that's the only 3. 14, 7. So yeah, times 5 squared times 7. So as we can see, we have 4 prime factors that divide that divide 8,400. So our number of p factors, prime factors, or divisors, 4. Num of square p factors. Well, we just have 2 to the 4. Well, we just have, this is just 2 squared squared. So we just have 2, right? We have 5 squared and 2 squared. So we have 2. Okay? And then finally, we have we can't forget our 1. So now we found all our values that we don't want. So the ones that have less than 4 factors. So 1, 2, and 3 factors. And now let's find the total number of divisors of 8,400. So I'm going to duplicate this. And then I'm going to select all of this. And then I'm going to delete it. And then what I'm going to do is we're going to just continue. So we already have the prime factorization of 8,400. So let's just directly apply the formula. So t of 8,400 is nothing but, well, let's see. So we just have 4 plus 1, 1 plus 1, 2 plus 1, and then 1 plus 1. Right? Those are just the exponents of the prime factors. And this just equals, well, we just have 4 times 5 times, this just equals 60. Okay, so this is the total number of factors of 8,400. And now, here we have a total number of values to be eliminated, which is 1, 2, 4. If we sum that, we just get 4 plus 2 plus 1 is just 7. So now we can just subtract 7 from 60, and we just get an answer of 53. So hopefully you were able to solve this, and have a nice day.